when we were looking at that continuously compounding formula, we were looking at with A of t is equal to P times E raised to the RT, the PERT. Remember, P represented that initial amount. So in this general formula that we have for growth and decay, we're not calling that P because it's not a principal. A P is the initial for principal, which applies for money. This A sub 0, that's going to be by initial amount. Just like you have your initial deposit, that's the initial amount. A lot of times it goes with population, it may be bacteria. So that A sub 0 is the initial amount. So that's my first variable. I still have my little e. My t is still time. Now, if you remember with PERT, R was your interest rate. Well, interest rate only applies to money or items. So what we're dealing with these other applications, we don't call it an interest rate in the formula. We call it a K value. And K is the constant rate of growth. But you can see this is just a variation of PERT. Initial amount times E raised to the RT power. But instead of calling it R, we call it a K, the constant rate of growth. Or it could be a decay as well. And again, A of T is the size of the population at any time T. So this could apply for growth or decay. If your K value is greater than 0, the population grows or increases over time. This is the growth or constant rate of growth. Sometimes they give you K, sometimes you'll have to find it in the problem. If K is less than 0, so if you end up with a negative K value, it decreases or it decays over time. So again, here's my PERT formula, but again, I'm expressing it A sub 0 times E to the KT. If K is greater than 0, this, remember, is your growth. And graphically, what's happening is it looks like this. As your X values are getting larger, so are your Y values. If you have a negative K value, again, this is your decay. So graphically, what's happening if you have a negative K value, graphically, as your X values are getting smaller, so are your Y values. So that's the difference graphically between a growth and a decay. Sometimes they'll give you a formula. Sometimes you'll have to set up your own formula using that PERT formula. So let's take a look at number 1. Based on data from the past 50 years, the world population of billions can be approximated by this particular function. So notice they're giving me the equation, where x equals 0 corresponds to 1950. So when you take a look at this particular formula, they want to know what is the rate of growth. Now, this is my initial population. That 2.5 is my initial population. The 1.0185, if you think about your other interest formula, you had your initial population times 1 plus R over N raised to the N times T power. So if N is equal to 1, we know we talk about an annual population growth, we'd have 1 plus R raised to the T power. Notice this is the formula that they are giving you with an N value equal to 1. So now look at what part A could be. What would the rate of growth be? It's 1 plus some particular R value. So what is the rate of growth going to be for this particular equation? It's going to be what? 0.0185. Or as a percent, what would it be as a percent? As a percent, it would be what? 1.85%. So any questions if they give you that particular equation, how you can determine what the rate of growth is going to be. So now part B, estimate the world population in 2045. Well, again, they're telling you that x equals 0 corresponds to 1950. So if I want to know what the population is going to be in 2045, what am I going to plug into this equation for x? I'm going to have to plug in the difference between 1950 and 2045. So what am I going to plug in for x? What value am I going to plug in for x? 95. So then g of 95 is going to be equal to 2.5 times 1.0185 raised to the 95th power. So then 2.5 times 1.0185, all raised to the 95th power. Oops. Let me try typing it incorrectly. So it's going to be about 14.264 billion. So any questions on that one? In what year will the population be double what it is now? So remember when we were talking about doubling money? If my initial amount was P, when I double it, it's going to be 2P. Well, my initial amount in the equation is 2.5. Because this is my P value right here. So that I can take 2 times 2.5, set it equal to 2.5 times 1.0185, all raised to the x power. So what am I going to do first to start solving for x? Well, what can I divide out of both sides of the equation? I can divide out of what? 2.5. So 2 is equal to 1.0185, all raised to the x power. What's next to solve for x? I can do what? Natural log. So I have the natural log of 2 is equal to the natural log of 1.0185 raised to the x. Now how can I get x out of the exponent? Remember, I can use that power property and I can pull x to the front. So I have the natural log of 2 is equal to x times the natural log of 1.0185. Then what? To get x by itself, what can I divide by both sides of the equation? I can divide by what? Natural log. So any questions on how I've solved that so far? So now when I type this in the calculator, I have the natural log of 2 divided by the natural log of 1.0185. So I end up with about 37.813. Does that answer the question? What is the question looking for? What's the question asking you for? In what year? Is that a year? 37.813? No. So how do you find out what year it's going to be? Well, remember, when x was equal to 0, it was year 1950. So what am I going to add to 37.813 to figure out what year this will be doubled? 1950. So I would add 1950 to it. So sometime during the year 1987 is when this population will be double than what it is in 1950. Okay? So 1987.813 or sometime during your year 1987. Okay? Any questions on that particular example? A wound problem. So a normal healing of wounds is modeled by an exponential function. A sub 0 represents the original area of the wound, and A represents the area of the wound after n days. Then the function is given by. So this is a case where they're actually giving you the K value, and they've already plugged it into the PERT formula for you. What should happen with a wound? Should it increase in size after a certain number of days, or should it decrease? Decrease. So is this going to be, notice you do have a negative K value there. Because with a negative K value, notice it is going to be decaying or it's going to be decreasing over time. So suppose that a wound has an initial area of 100 square millimeters. So what is this 100 going to be in terms of this particular equation? That's going to be my what value? It's going to be my A sub 0, exactly. So A sub 0 is going to be equal to 100. So I do have to plug in that 100 for the initial amount. So A of n is going to be equal to 100 times e raised to the negative 0.35 n. Remember, A sub 0 is just like the P in your interest formula, your PERT formula. So now we're ready to start answering the questions. If healing is taking place, how large should the area of the wound be after 3 days? So what am I going to plug into this formula then? I'm going to plug in what for n? 3. So then A of 3 is going to be equal to 100 times e to the negative 0.35 times 3. Should this number be larger or smaller than 100? Smaller. So I end up with about 34.994 square millimeters. So any questions on part A? So part B, how large should it be after 10 days? So what are we going to plug into this equation for n? We're going to plug in a what for n? 10. And we come up with 100 times e to the negative 0.35, so about 3.020 millimeters squared. Okay. So like I said, sometimes they'll actually have the equations set up for you. Sometimes you may have to actually write the equations yourself. So these are examples where they're actually giving you the equation. All right, so any questions on those? Again, all we're dealing is with PERT, except, again, we can't call it an interest rate because we're not talking about money, so we have the K value. A sub 0 is that P, it's the initial amount. All right, so any questions on that one? So let's take a look at spreading of rumors. So a model for the number of people in a community college who have heard a certain rumor, again, they're giving you the equation, where P is the total population of the community and D is the number of days that elapsed since the rumor began. In a community of 100 students, how many students will have heard the rumor after 3 days? So what is this 100? What variable am I going to plug? Where am I going to plug the 100 into this formula? Am I going to plug that in for N, P, or D? P. So P is equal to 100. And I want to know how many students will have heard the rumor after 3 days. So where am I going to plug in the 3? I'm going to plug in the 3 for D. So then I want to find my N of 3. So N of 3 then is going to be equal to 100 times 1 minus e to the negative 0.15 times 3. So I plug this in. Make sure you open up that set of parentheses. 1 minus your little e raised to the negative 0.15 times 3. So I end up with a decimal of about 36.237. What's my units here? What is this telling me? 36 what? People, students. Is it possible to have 0.237 of a student? No. So always round, when you're talking about people, round it to the nearest whole number. So about 36 students. So about 36 students have heard this rumor after 3 days. Okay? So any questions on that one? All right. So the next two are examples where they're not giving you the formula. The first step is going to have to be to come up with the equations ourselves. So a culture of bacteria obeys the law of uninhibited growth. When you hear this phrase, uninhibited growth, that's another word for exponential growth. or it could be uninhibited decay if it was a decay problem. So again, that means we're just going to be using that PERT formula, the A sub 0 times E raised to the KT. So right away, that's the formula that's going to be applying when you see that it's following the law of exponential growth or law of uninhibited growth. If 300 bacteria are present initially. So what is this 300 bacteria that are present initially in terms of this particular formula? What does the 300 represent? And which variable does that represent? A sub 0. So I know that A sub 0 is equal to 300. And there are 500 bacteria after 1 hour. How many will be present in the same culture after 4 hours? And then how long is it until there are 10,000 bacteria? So if I start plugging in what I know into my formula, A of T is equal to 300 times E raised to the K times T power. There's a piece of information that you need that they did not give you. What do I have to be able to know in order to find out how much bacteria there is after 4 hours? I know I plug in 4 for T, but what variable did they not give you? K. So sometimes they do not give you that rate of growth. So what you're going to have to do first is you have to find K. If K is not given to you, your first step is going to have to be to find K. All right? So let's talk about how I can find K. They gave you an amount of bacteria after a certain amount of time, because you're going to have to use this in order to help you solve for K. So I know that when T is equal to 1, I had 500 bacteria. Remember what this formula represents. It's the amount after a certain time period. So what I can do is I can take this equation that I started to write and set it equal to 500 and plug in 1 for T. So 500 has to be equal to 300 times E raised to the K times 1 power. So like I said, if they don't give you that K value, they're going to have to give you an amount after a certain time period to plug in to help you solve for K. So any questions on how I've set this up so far? So what's my first step to start solving for K? What's going to be my first step? Divide by 300. So I have 5/3 is equal to E to the K. Then what are we going to do to both sides? We're going to have to take the what? Natural log. So natural log of 5/3 is equal to the natural log of E to the K. So I know I can pull this K out of the exponent. So the natural log of 5/3 is equal to K. And remind me again, what is the natural log of E equal to? Natural log of E is equal to 1. So K is equal to the natural log of 5/3. So now I know I can finish writing this particular formula. A of T is going to be equal to 300 times E raised to the natural log of 5/3 times T. You do not ever use the K value as a rounded decimal to 3 places, because this is not your final answer. You have to leave K in exact form. This is exact form. The minute you round it in your calculators, it's approximate. You're then going to use an approximate answer in a formula to round another approximate answer. Your answers will get further and further away from what the actual is. So you never want to use an approximate value to then approximate another answer, which is what you're going to be doing in the end. Now, you can store this in your calculator so that you don't have to type in natural log of 5/3 in your formula. So on your calculators, if you type in the natural log of 5/3, there is a store button located right above the on button. Notice it's called, it's that STO with an arrow. So if you hit that STO with an arrow, notice an arrow appears on your calculator screen after the natural log of 5/3. You have the whole alphabet on your calculator screen. Some letters are in green, some are in blue. But the easiest letter to get to, instead of having to hit, notice K is located, where is K? In green. So instead of having to hit alpha, my open parenthesis, and store it in for that letter K, the easiest letter to store it in is for X. So now what happens is your calculator, anytime you type an X in on the home screen, the calculator is automatically dumping in the natural log of 5/3, taking out over 100 decimal places, because it's got all those decimal places stored in its memory. All right? So now we can use that particular value to answer the questions. All right? So now let's take a look. Let's find out how much will be present after 4 hours. So all I need to do is plug in 4 for T. So A of 4 is going to be equal to 300 times E. And what I do, so I don't have to keep on writing in that natural log of 5/3 over and over again, when I use that store feature on the calculator, I kind of write the letter that I stored it in and I circle it. That's just a reminder to me that it's stored. You can keep writing natural log of 5/3 if you want. So now I'm just going to type this in my calculator. So 300 times little e raised to the 4x, or wherever you stored that natural log of 5/3. So I'll have about 2,314.815 bacteria after 4 hours. Okay. So any questions on finding K? And then the next part, they want to know how long is it until there are 10,000 bacteria. So which variable am I going to be solving for in my formula? I'm still using my A of T is equal to 300 times E raised to that X. Again, that's my natural log of 5/3 times T. What am I solving for here in this particular formula? When they ask me for how long, I'm solving for what? T. So where am I going to do with my 10,000? I'm going to take 10,000 and set it equal to 300 times E raised to the XT. Remember, I'm not solving for X, I'm solving for T. What's going to be my first step to solve for T? Divide by 300. So I end up with 100 over 3 is equal to E raised to that natural log of 5/3 times T. Now what are we going to have to do to both sides to solve for T? We're going to have to do what? Natural log. So natural log of 100 over 3 is equal to the natural log of E raised to the XT. Again, I can pull that XT out of the exponent. And remember, natural log of E is just 1. Now, how do we get T by itself? What am I going to divide both sides by? I'm going to divide both sides by what? X, or that natural log of 5/3. Remember that X is what's stored in the calculator. So natural log of 100 divided by 3, divided by your stored value of natural log of 5/3. So it's going to take me about 6.864. And what's my units here? What's the time that it's being measured in? Hours. So it's going to take about 6.864 hours to get that 10,000 bacteria. Okay. So like I said, sometimes they won't give you the K value, and you're going to have to find it on your own. So any questions on example 4? The last example. The population of a Midwestern city follows exponential law. So again, that's another phrase that this is going to be an exponential growth or decay. So I know I'm going to be using this formula A of T is equal to A sub 0 times E raised to the KT. If the population decreases from 800,000 to 600,000, from 1998 to 2000, what will the population be in the year 2010? So is this going to be growth or decay? If my population is decreasing, what's happening? Is this going to be growth or decay? Decay. So what do I know about the K value when I go to find it? The K value is going to have to be what kind of number, positive or negative? Negative. It's going to have to be negative. Notice the initial population in 1998 is going to be what? What is A sub 0? A sub 0 will be my what? Which is 800,000. What are they not giving you again? They're not giving you what? Are they giving you the rate of decrease anywhere? Are they giving me that K value? No. So I'm going to have to find K. Before you can answer the question, you have to know what that K value is. If it's not given to you, you have to find it. So, again, they are telling me, however, in 2000, my population is 600,000. So they are telling me that in the year 2000, the population is 600,000. So the difference in years between 1998 to 2000 is 2. So I'm going to let T be equal to 2, because that's the year difference between 1998 and 2000. So just like I did in the last problem, I'm going to take 600,000, set it equal to my 800,000, which is my initial amount, times E raised to the K times 2. So what's going to be the first step here? To solve for K, what's going to be the first step? Divide by 800,000. So 600,000 divided by 800,000, I can simplify this to 6 over 8 or 3 over 4. Then what are we going to do to both sides to solve for K? You're going to do what? ln. Take the natural log. Now how do you get that 2K out of the exponent? We can now get that 2K out of the exponent. And remind me again, what is the natural log of E? The natural log of E is just 1. So 2K is equal to the natural log of 3/4. Then to solve for K, what are we going to do to both sides? We're going to divide by 2. So K is equal to 1/2 times the natural log of 3/4. Remember, natural log of 3/4 over 2 is the same as 1/2 natural log of 3/4. And what are you going to do with this number? You're not going to round it when you go to plug it in. You're going to store it in your calculator. Again, leave it in exact form, store it in the calculator. Do not use a rounded answer when you go to answer this question. So then I can type in my calculator 0.5 times the natural log of 3/4. Now remember, when I hit my store button, again, it's located right above on, I can hit X. It'll just override that previous stored value I had in there for X. And notice I am getting a negative number, which I should because it is a decay problem. So now that you have the K value, now you can finish writing the equation. So A of T is equal to 800,000 times E. Again, X is what's stored in my calculator times T. So now we're ready to answer the question. What's the population going to be in the year 2010? Well, if 1998 was year 0, what's the difference between 2010 and 1998? I'm going to plug in what for T? So I'm going to let T be equal to 12. So you guys go ahead and finish that for me. So we'll come up with about 142,383. Okay? Again, you're talking about the population of a city, not a bacteria or something like that, so you don't want to leave your answer in a decimal. You want to round it to the whole number. All right? So any questions on, again, so this is just kind of more applications of dealing with that PERT, that A sub 0 times E to the KT power. All right? Just dealing with it other instances besides just money. Okay? So any questions on those?